Hi, everybody. Welcome to my talk about going from rich text search to RAGs, Retrieval Augmented Generative Search. My name is Adam Volk. I'm a principal program manager at Microsoft. This talk might be interesting to you if you happen to work with PostgreSQL, if you want to learn how to employ recent developments in machine learning models into your PostgreSQL applications. So without further ado, let's go into the slides. We will be building a chatbot email helper, and we will start with basic search, go through full text search, then AI-enabled semantic search, and finally end up on Retrieval Augmented Generation, also short for RAG. Now meet Millie the Mailiphant. Millie is a helpful little being going over the PostgreSQL mailing list archives that you may have been using to ask questions about PostgreSQL, and she will be here to answer all of your questions about PG based on what she read on the mailing list archives. So the way to approach implementation of something like that, you would go to the public PostgreSQL archives that you can download and then load into a database, let's say to an emails table. And then you could start with a naive implementation where you can do things like queries with a wildcard search and enter what the user said, like write a headlog. And you would happen to find this email, which is PostgreSQL capabilities. But another user may say wall log, and this email is no longer being found. Another user may have entered 2 spaces, and again, the email would not be found. Now, you may say that you built it wrong. You can use the wildcard search also between the keywords, and that's true. That would give you the first email again, but that's not very efficient, and also the amount of permutations you would have to do to capture both this and any other form would be just too much to implement. So what you can do to remedy this is to rely on full text search that happens to be present in PostgreSQL. So to enable full text search, we can alter the emails table, adding a TS vector column, and TS vector here stands for text search vector, not pgvector. And what we will do is we will take the subject and content. We will assign the weight A to the subject, weight B to the content, concatenate them together, and store them as a generated all results column called TS. Now, when you do that, all the emails will be parsed, and we will have this TS column that looks something like what you see on the screen right now. And now if the email has, for example, the email talks about PostgreSQL capabilities, and in the body it has capability, both occurrences of this word would be brought down to the common form kappa BL, with the location of each occurrence being noted next to the word and the weight that we assigned being also there. So for example, any form of the word log, which includes logs, log, logging, etc., will be enumerated. But what is the number standing for? The number is the end token in the email in our case. So I brought this from the previous slide to have it handy. Log 15B, 35B. This is the 15th token of the email, in this case logging, 35th token of the email, in this case log. And how do I know that it's the case? Well, with PostgreSQL, you can actually log into how things work. That's the benefit of having an open source database. You can call the tsdebug function, which has been implemented by the developers of the database, that shows you exactly how the document is being tokenized. So we can see that the 15th token is the ASCII word logging that got stamped into the lexeme log. And this is how you can confirm these numbers to the content that you have been parsing. Now I did the highlighting manually, but you can also ask PG to highlight it using a user-defined function, UDF for short, called tsHeadline. And it will output by default the HTML bold tags around all the places where the content matches. And you can of course change what it outputs around it if you have a different app. Now, full text search does a ranking. So this number, the more relevant the result, the higher the number. And the complexity of this query is to show you how the output of the TS rank column itself and the web search to TS query user-defined function is just a nice way to write something in English and have it translated into this complex query language that the extension uses to find all what you said. And it understands things like cat or dog, and it would translate that to the logical OR operator, so it knows that it's either this or that. Okay. With full text search, of course, it's not cheap. It still takes time. So what you can do to speed things up is you can create indexes on it using, for example, a GIN index. So create emails index on the email table using GIN, and we can see the above query went from 3.5 milliseconds down to 0.062 milliseconds, which is a significant improvement. So what is semantic search? Now that we know how to search with full text search, we still won't get all the permutations that user asks. So for example, if I enter durable transaction log, that's the same thing as write ahead log, but a full text search will not be able to make a connection, but a large language model would. So to use semantic search, we need to work with vectors. And a nice way to work with vectors in PostgreSQL is to use the pgvector extension. And what you typically store is embeddings. Embeddings are created by large language models. And the distance between two embeddings, so two vectors created by large language models, will show a similarity between them. So if you create an embedding for a transaction log or durable transaction log and an embedding for the write ahead log, the distance between these two things will be shorter than from a cat or a dog. So that's what these models will be able to encode. Now, searching vectors is still costly. So there are multiple ways of indexing that. There's the inverted file index and hierarchical navigable small worlds. These are available in pgvector. They have different trade-offs for performance and recall, so read into them on what's more important in your specific use case. So now that we know how to work with vectors in PostgreSQL, how do we get embeddings? And if you are using Azure Database for PostgreSQL Flexible Server, you can actually use the Azure AI extension, which has multiple functionalities for cognitive services, for for extractive summarization, language detection, key phrase extraction, translations, and you can also create embeddings. So let's put this together. We start by creating a vector extension, which is pgvector, the Azure AI extension. We create the endpoint. We set the endpoint to what we defined in our Azure OpenAI deployment. We set the subscription key, and then we alter the emails table as we did with full text search, but this time adding an email embedding column of type vector, which is pgvector. of dimensions 1536, which matches what my deployment returns, generated always as a call to Azure OpenAI, create embeddings using text embedding ADA O to deployment, where we take the subject and content, concatenate them together, trim them to roughly 8,000 characters because that's the limit of my deployment. And now that we have this, we can search over all our emails using semantic search, using this inner product operator to find the distance between whatever email and what is the write-ahead log. And if you remember from the first slide, we had up to one email, which is the first one that had the exact occurrence of write-ahead log, but we didn't see the remaining ones. And here we can see that the model was able to make the connection. And of course, semantic search takes time. So what we can do here is create an index, like we said, in this case, HNSW for inner product. And we can see the time of the above query going from 10 milliseconds to sub 1 millisecond. And since emails are big, you can see how we could use, for example, summarize abstractive to know what the email is talking about. So if I concatenate 5 emails that are semantically close to what is the page size and ask the model what they talk about, it describes them, but also you can see this part, specifically the 8 kilobyte page size of PostgreSQL. So it did find something that answers this question in the content. So what is RAG? RAG is Retrieval Augmented Generation, and if you ever used a large language model like ChatGPT, you know that it learned on a lot of the data from the internet. So if you ask it questions like, what's the write-ahead log? It will answer that, but it may as well tell you how it works in MySQL, SQLite, or Oracle, for example. And it may make some weird connections like that. And even if you told it that you want to learn specifically about PostgreSQL, it might tell you how that worked in the 90s, not today, because that's overrepresented in the data on the internet. So what you want to do is you want some way to tell the model, hey, ground your answers in this set of documents and don't go over it. So you could write a simple prompt like this saying, answer the question using the document. And if you don't know the answer based on the document, say, have you tried turning it off and on again? And then you could add the content of the email as the document, and the model would see the question, what is the write-ahead log, look at this email, and it would be able to say, what is write-ahead logging more conventional way of assuring atomicity, etc., because the answer is in the document. So the big query here is not that important. What I want you to remember is that that's the way you grab an email and all the replies to that email, because the question is what's relevant to our search, but the answer is likely in the email chain below. So without further ado, let's skip into the demo and see how to put all of that together. So I built this Rails application and loaded it with some emails from the mailing list archive, and you can see there's a bunch of them here, like this one talking about passwords, and a reply that has an answer that somebody wrote a blog post to this on how to recover passwords. So how does it work? We have this email class that has this big query that you saw in this semantic thing. So let's use this to find all emails that talk about what is wall. And this is our Rails console. And you can see the big query being executed. And I have this context, which is a huge email. And I don't know what it is, but I could ask a machine learning model to summarize it. And I actually implemented that with a call here to in the email class that uses Azure Cognitive Summarize Abstractive to summarize the content of the email that we just grabbed. This will take a while to concatenate all the text, go over the internet, and return back a short summary what the document describes. So that's cool. Let's go further. We want to ask questions to the model. So we have also this chats interface where I can ask, what is the wall? And it will be going over the internet, asking them, like grabbing all the emails, chunking it, sending it over the internet, and hopefully getting back to us with an answer that the write-ahead log is a standard feature of PostgreSQL that ensures durability. So it works, but how? We have this the Mailiphant class, where we define that if you have no idea, have you tried turning it off and on again? And then we have this brag pattern. So we need to split our data because my model happens to have a limit of tokens up to 4.5k tokens per request. And if we look at using this Ruby method, how many tokens this above email has, we learned that it's over 7,000 tokens to get the answer. So that's too much within my limit. So I need to do this in chunks. Instead of one request, I'm going to do multiple. And for every request, I'm going to tell the model, hey, you're Millie, the playful Mailiphant that knows everything about PostgreSQL. Answer the question based on the context. And if you don't know the answer, say no idea, which is have you tried turning it off and on again. Then we pass the content and the question, and we grab the list of responses, reject all the no idea ones, and return the first one that looks good. So how does this work in code? Let's run this in the Rails console. You see the big query being executed to grab the context. You see each chunk, as I described, being processed because it has to fit in my token limits. And there are multiple replies, and one of them is the one that we selected and presented to the user in the chat. Now I can ask it anything, like I can ask it, I forgot my password, help, and it will process again. And some of the chunks may not have an answer, so we will get, have you tried turning it off and on again? And we ignored that. But others are good, and we get an answer that's acceptable. We can also ask it different things like how to store binary data. And it should tell you something about, for example, byte arrays in PostgreSQL. Or something else, depending on the emails it finds and the decisions that the model takes based on the data that it's provided in all the chunks. We will let it run for a while as we prepare for the next one, which is when do I manually vacuum? Okay, unfortunately, these things are undeterministic, but we have binary data is best stored in byte A data type in PostgreSQL, and you can see a lot of them had answers. So let's ask it, when do I manually vacuum? And it tells us that manually vacuum when dealing with temporary tables, because auto-vacuum, auto-analyze cannot process them, which is a great answer. And the interesting part is, if you noticed, in my query here, I limited emails to above 2020. And let's remove that limitation, reload the Rails model, and redo this query and see what the model tells us. Now we are also reading all the emails that I have loaded from the 90s, like I said in the example where I mentioned ChatGPT, and I expect it to provide not so good answers anymore. And it tells me that it is common practice to set up cron jobs to vacuum databases nightly and things like that. And the reason it does that is because in some of those emails, they are so old that auto vacuum was not a thing. So that's why you might want to do this hybrid search approach, where you take both things like basic search, column filtering, and full text search to pre-filter the data set. And that helps you to save time on indexing, time on searching through all the vectors, because vector similarity search is costly operation. So you can benefit from other methods of searching. And maybe as a final thing to show, we can see how it behaves if we ask a question in a different language. For example, j'oubliais mon mot de passe, aide-moi. So I forgot my password, help me, in French. And you can see in the query that it also did the query in French, so you don't need to translate what the user typed in the search field. And it told you, we actually saw this email. Hey, the answer to this question in French is, you might want to read this blog post that tells you how to recover a lost password in PostgreSQL. And you can modify the prompt to have it answer in the same language as the user asked the question. And in the case of all these answers I had, where there were a lot of them and I just picked the first one, you can also grab the full list of answers, send it to a model and say, hey, pick the best answer out of these. And that would be a smarter way of doing that, so you have some ideas on how to improve this. So hopefully with this, you feel more encouraged to explore how you can employ AI and vector similarity search within your PostgreSQL-based applications, and see how easy it is now to do this quickly in your apps. So thank you for watching the talk. It's been a pleasure. See you around.